Since the dawn of civilization, man's history has been tied to his use of metal. The progress of today's world relies more and more upon metal products formed or molded into every conceivable shape. With the advent of the space age, the contribution of so-called sophisticated metals has opened the door to a new horizon of technology. There are many methods of shaping metal products. This film tells the story of open die forging. Open die or free-form forgings are made on hammers or presses employing dies that are smoothly shaped but not completely restricting metal flow, taking advantage of the plasticity of metal at forging temperatures. Forging is undoubtedly the oldest mechanical forming method in the metalworking art and has its roots in the traditional blacksmith operation. Longfellow wrote, "Beneath the spreading chestnut tree, the village smithy stands. The smith, a mighty man is he, with large and sinewy hands." Early American history is a reminder of the important role hand forging played in the nation's growth. In due course, the blacksmith was aided by power developments beyond his own physical capacity. Today, huge manipulators, mechanical devices for handling ingots during forging do the work of the blacksmith's hands and arms. Modern hammers or presses exerting millions of pounds of force replace the blacksmith's hammer. Infernos of heat take the place of the blacksmith's hearth and bellows, and today, a wide range of sophisticated alloys are formulated to specific properties to match the end product requirements of the customer. Iron and steel, it is said, are close to being immortal. After careful classification, scrap is used over and over again. The sound of the word scrap contradicts the sophisticated technology involved in its use. The process begins with samples undergoing laboratory analysis and classification before melting and subsequent reprocessing. This analysis is repeated throughout the melting cycle to make sure the heat of steel contains the right amount of each element specified. Alloy additions are made to the molten bath as a result of these laboratory tests. Today's needs for super steels has produced constantly expanding demands for technicians in metallurgy. In addition to college-trained technicians, laboratories of the forging industry offer to high school graduates the opportunity of entering the metallurgy field. Many companies sponsor in-plant and advanced formal training programs. The highest purity metal for forgings can be produced by electric arc or vacuum furnaces, and subsequent vacuum degassing, vacuum arc remelt, or electro-slag remelt. The liquid metal is tapped into a large refractory lined ladle and moved by powerful electrically driven overhead cranes from the electric arc furnace to the vacuum degassing chamber. Refining steel in a vacuum helps to rid it of certain deleterious gases, such as hydrogen, oxygen, and nitrogen. The reduction of these gases makes it possible for the forger to meet the more rigid customer requirements of jet engines, die steels, high-speed rotating equipment, and nuclear applications. Inside the vacuum chamber, the steel boils very much like candy fudge. Throughout every phase of steel making, tests and samples are continually examined to ensure customer satisfaction. The material required in forging may range in size from small billets or blooms of a few pounds to huge ingots weighing several 100,000 pounds or more. The steel industry has contributed to the success of the open die forger by working in close harmony to supply specified raw materials. Modern metallurgical research and quality control laboratories throughout the forging industry daily search for still better utilization of the potentials of metal. Forging enhances all of the basic mechanical characteristics of metals, such as ductility and tensile strength. Here, a machine piece under production is tested for these properties by measuring precisely the amount of tension it will withstand before rupturing. Maximum ductility is forged into metals to be used in such high-stress application as helicopter parts. Another characteristic of forged metal is its ability to absorb impact. This test measures the amount of energy absorbed in fracturing a prepared sample. Here, the impact is shown in stop-motion photography. High impact absorption qualities are required in applications where repeated shock is encountered. This Rockwell test measures the hardness of the forged product. The indentation size is used to determine material hardness. Particularly hard and tough metals are called for in many applications in mineral handling, steel production, and fabrication. All these properties of metal are improved in forged products by refining grain structure. Forging is, in reality, the improving or refining of grain structure. But modern forging is more than technology alone. To the sounds of hammers and presses, the forming of shapes is a symphony of color. The modern forging plant stocks or melts a wide variety of popular grade carbon, alloy, stainless, tool steels, low alloy, and special super alloys. As a result, forged products can be produced to almost any metallurgical specification more rapidly than cast or fabricated parts. Emergency requirements can often be satisfied in a few days. Typical parts produced from an inventory like this are high-quality forged rings. A solid steel block of exact weight for making the ring to be forged is cut and then heated to forging temperature. When the metal block has been flattened and rounded, a slug is punched from the center. At this stage of shaping, the ring is colorfully known as a donut. Manufacturers forge rings measuring in diameter from inches to many feet. The forging process produces a solid ring with unbroken flow lines. This smooth grain flow adds strength and toughness superior to that of cast or welded rings. As in most forging operations, this process of preforming the hot metal to desired shape is accomplished in a series of heating and forging operations. Rings are used extensively in anti-friction bearings, in rocket and jet engines, in gears, tires, and turbines, in missiles, and in many other applications that require high-quality circular shapes. For larger rings, the prepared donut is rolled on one or more ring rollers depending upon final dimensions required. As the ring revolves between the main roll and the pressure roll, its diameter grows as the edging rolls control its width. Typical of the application of modern technology to the forging industry is this ring expander as a final sizing operation. With this automatic equipment, exact dimensions greatly reduce the amount of final machining. Most forgings are given some form of heat treating before shipment. The particular process is chosen to produce the necessary mechanical properties and to assure satisfactory service performance. One form of heat treatment, called annealing, is specified when the product must be relatively soft for machining. In this case, a large weldless steel ring is being machined for a solid propellant booster to precision tolerances. Basic ring forgings may be cut to various shapes or supplied as blanks to the gear cutting industry. They may support thousands of tons in manufacturing processes or become the dies used in pipe rolling or other fabrication equipment. Throughout the petroleum and chemical industry, many high-pressure pipe couplings are ring forged. And the stresses of modern jet engines demand the quality of many forged components. Multiple diameter or hub forgings can be quickly supplied from stock dies, providing forged quality and close tolerances economically. Another basic forging operation used to produce circular hollow parts similar to rings, but up to many feet in length, is known as hollow forging. A hole is pierced through the center of a prepared billet with a series of punches. The mandrel, a bar that is inserted into the cavity of a prepared block, is used in conjunction with a press to expand and lengthen the forging wall. This forging, a liner for the extrusion industry, is produced from extremely hard tool steel. To aid in rough machining, it is annealed or softened by a hot salt bath. Liners like this one, being precision bored, are used in extruding a wide range of rod or tubular material, including brass, copper, aluminum, and plastics. This large liner will be used to produce copper alloy rod, extruded under extreme pressures of over 11 million pounds. A wide range of other products, ranging in size from 1 to many feet, are mandrel forged. Included are large gun tubes, chemical retorts, reactor chambers, pressure vessels, rings, and gear tires. The diameter and length of mandrel forgings are practically unlimited. Roll sleeves like this are precision machined and used in a wide variety of manufacturing rolling processes. By using a sleeve over the exterior surface that is subjected to wear, only the sleeve section needs to be periodically replaced. This mandrel forged sleeve has been heated to the precise temperature which produces sufficient expansion to allow fitting over the roll surface. When the sleeve has been placed over the roll and cools, contraction holds it in place. To remove a worn sleeve, the process is reversed. This exacting process, known as shrinking on sleeves, is another outstanding contribution of the open die forging industry. Sleeve and roll combinations are machined to whatever finish is required. They are used extensively in rolling steel, forming metals, as well as in the linoleum, plastics, rubber, and other industries. Hollow forging was called upon to provide the optimum strength characteristics of today's super steels, used in missile cylinders and many other smaller components. Many forgings are part of the Navy nuclear program. Special applications have included radio telescope axis gear. And hollow forgings are widely used in a host of high-pressure applications, including chemical retorts and reaction chambers. A wide range of special products having the toughness and durability required in their application are forged on relatively small hammers. The craftsmanship of these specialists is developed over many years, and the growing need for their skills offers the opportunity for young men to enter one of the highest paid crafts. Crane hooks are subjected to intense operational stress and must provide maximum strength, toughness, and resistance to fatigue in those areas subjected to the greatest shock and stress. This hot bending operation under the hammer achieves the necessary optimum grain flow. Even in complex shapes, forgings can be produced to extremely close tolerances. thereby frequently reducing to a surprising degree the need for machining. Although rough or semi-finished forgings are regularly ordered, most manufacturers combine machining and finishing facilities with forging and heat treating to provide a complete service. The crane hook, a familiar item, is manufactured by the open die forging method. It is representative of thousands of specialty items essential in the operation of practically every industry that must be preformed by this forging method. Specialty forgings can be complicated in shape or be plain flats for knives on severe applications, or the jaws for powerful bending or shearing presses. Slabs or plate sections like these, heavier or thicker than can be produced by rolling operations on a slabbing mill, become heavy plate sections for fabricated parts, or dies for the closed die forging, plastic, and die cast industries. As with other forgings, they are finished to required size and shape by the machine shops of the forging company. The largest forgings are usually forged directly from ingots that are never allowed to cool until the forging is finished. For the heavier forgings, powerful hydraulic presses are used, in which the heated metal is squeezed into the desired shape. This process, called upsetting, shortens the ingot axis while increasing its cross-section and at the same time compacting the center. This configuration would be necessary in such products as discs, heavy sections for rotor and generator forgings, stub ends, and gear blanks. During forging, the manipulator operator controls the movement of the ingot, often weighing many tons, with as much precision and dexterity as the early day blacksmith handled a horseshoe with his tongs. Forging shafts employs the method known as drawing out or forging solid. This method will produce a forging whose length is considerably greater than its diameter, by reducing the cross-section and simultaneously elongating the ingot or bloom. Here, swage or semi-rounded dies are used to produce a more perfectly rounded forging. These typical forgings may become pinions, dies, machine tool parts, or satisfy a variety of other high-stress requirements. The open die forge shops producing today's largest forgings have continued to increase the capacity of their equipment to match the demands of today's technology. Presses with capacities up to 14,000 tons are in operation to handle giant forgings. Ingots weighing nearly 800,000 pounds have been cast for heavy industry applications. Electrical equipment manufacturers are major users of shaft forgings in massive rotors for generating equipment, as well as large electric motors wherever ultimate reliability is essential. Other applications include ship shafts for propulsion drives of large ocean vessels, massive multi-throw crankshafts, and huge rolls used throughout the metal forming industry, as well as a wide cross-section of manufacturing processes. The heat treating process further refines the grain structure, removes residual stresses, develops the strength and ductility of the steel to make a good forging a better one. Where unusual characteristics are demanded, special heat treating processes are available. This vertical quench assures straightness and product uniformity. Shafts, like other forgings, are brought to their finished or semi-finished stage on the many turning and boring lathes, planers, milling machines, slotters, grinders, and vertical boring mills. And as modern technology creates new demands, forging capacities and capabilities have kept pace. Never before have the opportunities for high school and college graduates been greater. With an eye toward the future, the open die forging industry has developed extensive apprentice, on-the-job, and technical training programs. College graduates find increasing opportunities and challenging careers throughout the industry in such areas as computers, production control, accounting, engineering, melting and forge plant operations, metallurgy, and management. Participating in such a basic industry, which supplies practically all other industries with forged steel products, provides the individual with occupational activity which he will find exciting, challenging, and financially rewarding. Typical of the ever-expanding technical advances in the forging industry is this spray quench heat treating process. This large roll, for a steel rolling mill, is being surface hardened to desired characteristics and hardness profile. Finished rolls, as with all forgings, are subjected to a series of quality control tests. This scleroscope hardness test assures that the surface of these rolls meets required specifications. But the area below the exterior surface also undergoes quality tests. Ultrasonic test equipment assures consistent metal composition and freedom from internal flaws. Wherever industry demands ultimate quality, such programs of quality control assure that open die forgings represent the highest standard of reliability. Rolls for the metal forming industry in hundreds of applications and sizes are a major contribution of the forging industry. And when an electrical generator surges into operation, its massive rotors, produced by open die forging, withstand the stresses of peripheral speeds equal to modern jet aircraft. And like the electricity that flows out across miles of power lines, so free-formed forgings flow into almost every aspect of our everyday life. Another industry relying upon forged products is railroad transportation. The forging of trains, subway, and other axles capitalizes upon the efficiency of automation and computer control. The quality forged into this metal will assure its dependability as it operates in yet another industry that relies upon the open die forger. Crankshafts for large diesels and other engines are produced from forgings to assure ideal grain and stress characteristics. As technology strained the limitations of exotic metals to the ultimate in nuclear applications, forgings were essential. From the special metals, alloys, and forging procedures developed, a wide range of other industries now benefit. Forgings were silent partners in many applications that protected man in his venture into space. And as tomorrow's world is forged, the products that shape our world will rely upon the contributions of open die forging for ultimate quality in metal fabrication. strongest metal product is a forging.